to talk about computing risk econ sampling.
Thank you, Hui. Okay, so I'd like to start by thanking the organizers for having me here. It's my first time at the RESIM conference, and I will talk about some joint work with a student in Stockholm who finished this year, Jan Svensson, and this is about risk measures, computing risk measures by importance sampling. So here's a little outline. We'll have a short introduction about some of these risk measures, and then I'll spend some time on sort of the asymptotic theory, and that will involve quite a bit of empirical processes. And then at the end I will come to an example where we do this in a heavy-tailed setting, which is sort of a regularly varying case. But just to set the stage, what we are interested in is sort of some property of a distribution that relates to the tail of the distribution. So we have some random variable x, so that could be, say, a loss of a financial portfolio or whatever you like to think about. And I will denote by f the distribution of x and also the tail. So I don't put a bar on the tail, but I let f be the tail. That's just for you to have something to think about during the talk. Right, so you keep on your toes. But for me it will be a convenient notation, so I will use it. And the thing why it's convenient notation is that I will have some functions that are like distribution functions, but they are not probability distributions, so they don't have total mass 1, and then it's sort of inconvenient to take 1 minus. So that's sort of the point. So we have some quantiles, which if you're a finance person you call value at risk, that we might be interested in. So that's the smallest number such that the tail is less than p. And we can have other things like sometimes called expected shortfall, which is the average of the quantiles from say 0 to a level p. And you can think of other sort of properties of the distribution that relates to the tail of the distribution. But these are the things that I will be focusing on. And then pretty much the story is as follows. So what I will say is that if you want to compute this by Monte Carlo, say it can be inefficient because you don't get so many samples out in the tail, so you need to sample a lot in order to get some decent accuracy. And so then you can use importance sampling to send more samples out in the right region. And then the main message here is basically that as long as you can design efficient algorithms for computing rare event probabilities, you can also compute these things. And the difference of computing these things compared to probabilities is that this is sort of a nonlinear function of the distribution compared to probabilities, which is a linear function. And that's sort of the main message. And then I will not say anything about how to design these rare event probability algorithms, because that's what everybody else is talking about, more or less. So I will not say anything about how to do it. Just trying to reduce the problem of these things to that of rare event probabilities. Okay, so here is in writing, if you can design efficient importance sampling for probabilities, you can also compute these things efficiently. And this is somewhat true, at least. Okay, so here's how it works. So first, just say how you would do it by Monte Carlo. So if you're interested in a quantile, this is sort of a typical way you would do it. So you start by sampling independently from your distribution, and then you form the empirical distribution, let's call it bold Fn. And if I put in a set, I interpret this as the distribution. So that's sort of the point measure that put points masses of size 1 over n at the locations of my sample. And if I put in an x, that means I plug in the set from x to infinity. Okay. And then you just use this empirical distribution in place of your original, of your true one, right? So you estimate your quantile by taking the quantile transform of the empirical. What does this mean in practice? It means that you will get one of your order statistics. And which one will you get? Well, then you just have to think a little bit, and it will be the integer part of n times p plus first largest order statistics. So these are ordered, x1n is the largest one, and then it's sort of decreasing. And of course, then you see the typical problem of Monte Carlo, that if p is small, then typically this will be sort of one of the largest observations, and that fluctuates a lot. So this will be, you need a large n to cope with this. Okay, in the picture, here's the sort of empirical tail going down to 0 with step size 1 over n, and it jumps precisely at the order statistics. So if you go in at the level p, say over here, you see that you will always get to a point where this jumps, so that will correspond to a specific order statistic, and that's where your estimate is, right? Okay, this picture is, I didn't make it myself. There was a diploma thesis student from ETH in Zurich who came to visit us, and he worked a little bit on these problems too. So he constructed these pictures because I didn't know how to do it, but the notation is slightly different, so you shouldn't look at the symbols there. Okay, when you do say expected shortfall, you do the same thing. You take your independent sample, you form your empirical distribution, and instead of the true distribution, you put in your empirical. Right, so in this, taking the average of the quantiles from 0 to p, you will just plug in your empirical quantiles. And what happens then is that you will get like a sum of this form. You sum up the largest integer part n times p divided by n, and then you have a little additional piece. And this formula takes you maybe 30 seconds to digest, so the picture takes only a couple of seconds. So that's much easier. So here's the quantile, empirical quantile function. So that's the previous one. The previous one was the tail, now I inverted it. So I have the quantile function. It jumps then at 1 over n, and on the y-axis is the order statistics. So when you integrate this from 0 to p, you get the sum of these rectangles, right? And the rectangles have width 1 over n and height, which is the order statistics, which is just what's on the previous one. And then the last one, if here is p, it's very hard to keep this very still. But if that is p, the width of the last one is a little bit smaller than 1 over n. Right? So that's why you get here p minus the last point. So that's the width that is slightly smaller than 1 over n. Okay. And so that's your sort of standard Monte Carlo version, and then that will suffer sort of from a problem that you need a large sample size. Now, if you see a little bit in the literature for computing, especially for computing quantiles, this is sort of a type of scheme that you often see, which is also based on being able to compute probabilities efficiently. So this is works in the following way: that what you do is you guess a value for your quantile, say x naught, and then you try to compute the probability of x being greater than x naught. And you do this by importance sampling, so you can compute the probability efficiently. So that gives you an estimate for this probability. Now this can be either too large or too small. So if it's too large, means we guessed a too small value. So we need to increase our guess. So then say take your new guess as twice the initial guess. If it's too small, well then we guessed at a too high value, so you decrease your guess. Say you take half of your initial guess. And then you continue like this until you have sort of some guess that is smaller than your quantile, and you have one guess that is larger than your quantile. At least you have a lower and upper bound. And then you use a bisection method. You split in half, and you work your way through computing probabilities until you seem to converge, and that's your estimate for the quantile, for instance. And you could argue that this is efficient because what you're computing is probabilities, and so if you do that efficiently, then this will terminate reasonably fast, and then it's also an efficient algorithm. It doesn't give you really a good level of confidence for where your estimate is, and doesn't really provide you a good way of computing other functionals of the tail, like expected shortfall, for instance. But so I will not continue talking about this. I'll just mention it, and I'll say so. What seems to be the most direct approach. So this is the direct approach. So what you do is with importance sampling, you select sampling distribution. Let's call it G. So you generate your samples independently from the sampling distribution, and then you form your weighted empirical distribution. So instead of putting weights 1 over n at all the locations of your sample, you put the likelihood ratio weights. Right? So this is precisely what you do when you want to compute probabilities. And so I call this Fn hat. So this is sort of the weighted empirical distribution that you get by sampling from G, but it's trying to approximate the tail of F. Right? And then when you want to compute this quantiles or average of quantiles, you just plug in the quantile transform of this instead of the true thing that you're instead of the true distribution that you don't know. Okay, so what happens then is that, well, this will also jump down at the order statistics. The graph looks just the same. It's just that the jumps are the size of the weights and not just 1 over n. So that's the only difference. So what you will get is you will also get one of the order statistics, but which one is it? Well, it will be the case one where k is the smallest number such that the sum of the weights exceed p. And then I call W the weight, so Wj is the weight of the corresponding to the jth largest outcome in my sample. Okay, so the picture is of course the same, but now actually the notation is pretty much consistent. Just that now it jumps with size which is equal to the size of these weights instead of 1 over n. Okay. And then of course the other one, expected shortfall, works precisely the same way. You plug in your empirical quantile instead of the true quantile, and then the base of your rectangles will be the size of the weights instead of just 1 over n. Okay. So it looks just like that. Okay, so that's sort of a direct approach how to compute this, and of course the main part then is to select your sampling distribution G, right? As always in these kind of problems. Okay, if you like, you can put this in a slightly more general context, that you're computing some functional of the distribution by plugging in an empirical distribution coming from importance sampling. Right? And so if you're interested in computing an expected value or a probability, then this functional phi is linear, which is quite nice. Then you will have unbiased estimators, for instance. Whereas when you do quantiles and expected shortfall, this will be nonlinear. So this causes additional problem. For instance, it introduces bias. And what I will do pretty much is ignore this by sort of working with a linearized version of phi. Okay. And I will get back to this a bit more sort of as we go along. So the main point when you try to compute these things is, well, you want your empirical sort of sample based on importance sampling to provide an accurate description of the distribution in the region that you're interested in. Right? And the way, sort of the informal way to argue that it's enough to look at algorithms for computing rare event probabilities is pretty much the following. If you're interested in some function of the distribution which is out in the tail, and then say you take some point before the tail starts or before the region starts. So say if you're interested in a quantile, you take a point slightly below the quantile, say. And then when you want to compute probabilities, what you like to do is approximate the conditional distribution given that you exceed that point. And if you can sample from that, that should also be good for computing any other kind of functional of the tail. And that's pretty much the story. Right? And then it's a matter of how to phrase this and how to argue, and that will sort of be in the details to come. Okay. So some asymptotic theory. So the asymptotic theory, I will give you sort of two levels of overview and then some details. So here's the highest level of overview, and then next slide will be a slightly more detailed level of overview, and then I will provide you a few details. So here's the sort of main weak point of this talk. So what I will do is I will first send number of samples to infinity. And this is somewhat in contrast to what you typically do in these kind of problems. We like to sort of think of n as fixed and send say your probabilities to 0 because we think of having a fixed computational budget. And I would like to do that too, but I don't really know exactly how. So I will do this as a sort of first step, right? When doing this eliminates some sources of errors, and I'm hoping these sources of errors that are eliminated are sort of smaller order, so they are not the ones that are responsible for most of the variance, right? So what will happen is we will have a central limit theorem as n goes to infinity. And in that central limit theorem, there will be an asymptotic variance that I call sigma squared p that depends on the level p of my quantile or expected shortfall. And then I will study this, how does this behave as p goes to 0. So I'm trying to be honest with you that I'm not so happy with sending n first, but I will do it anyway. Right? Okay, so here's slightly more detailed overview. What you will look for is that your empirical measures, these empirical measures based on importance sampling, that they satisfy central limit theorem, so that if I center with a true distribution, this will converge weakly to some centered Gaussian process. And I view this sort of in a empirical process setting, so I can plug in any function into my measures there. And then, so that gives you sort of a central limit theorem for linear functions, or for, yeah. And then when I work with nonlinear functions, I will sort of apply a delta method. So when I apply phi of fn and I center by phi of f, this converges also to some random variable, which I call phi prime of z. Okay. And then I have a central limit theorem for my estimator. And then it's the asymptotic variance, so it's the variance of this guy that's called the sigma p squared. And that's what I will study as p goes to 0. And then I will say, well, so what is good here? I will say, so roughly, what I want is my second moment to behave roughly as the quantity I'm estimating squared. So I would like so my GNs, my sampling distribution, to be such that the variance of this guy, the asymptotic variance, behaves roughly as the quantity I'm estimating squared. And then if you want to do it on log scale or not, well, you can decide depending on, and that of course depends also how quickly does this actually grow with p. Right? So now my quantities will not go to 0 because they're not probabilities, they will go to infinity because they're quantiles or functions of the tail. Okay, so a little bit on sort of the framework for doing this. So here are some preliminaries from empirical processes. So you look at a class of functions f that you want to plug in your empirical distribution, and then you view your empirical distribution as a map from the class of functions to the real numbers by just plugging in the function into the empirical distribution. And the empirical process, which is then the centered and normalized empirical distribution, is then viewed as a map. So it's a map from your sample space into L infinity of f. So it's like a bounded stochastic process in f. And then you call this class f Donsker, say if you have convergence in this function space L infinity of f. And z is your limiting process. So the classical result tells you that for empirical processes, if you take your class to be the indicator functions, then you have convergence here to a Brownian bridge z. Right? So that's sort of the classical Donsker theorem for empirical processes. Okay, when you do importance sampling, it's pretty much just identifying what's going on. So if G is your sampling distribution and I let W be the likelihood ratio, then what we are studying is the weighted empirical measure. So if you plug in some function into that, you get just the sample mean of the weights times the function evaluated at your x's. And so you can view this as Gn. Gn is the sort of non-weighted empirical measure based on sampling from G's. Right? So you can just view this as Gn, where you plug in the function w times f. So it's, yeah. So if you have, so what you're looking for, so in this notation, is that you have a central limit theorem for your weighted empirical measures for classes f in some class. This f script a will be, in our setting, the indicators where the left point is at a. So you're looking just on functions or indicators from, say, b to infinity or b to c, where b is greater than a. So you're just looking at the tail, basically. So you have central limit theorem precisely if w times this class of functions is g-Donsker. So that's sort of the thing you have to look for. And a sufficient condition for that is just that under your sampling distribution, the second moment of the likelihood ratio weights times the indicator is finite. Okay, so that's not a very tough condition to satisfy. And the main object that comes into play now is, because we will study this central limit theorem, and remember what I will focus on is the variance of this limiting process. So the important thing that comes in is the covariance structure of this, because this is centered Gaussian. So the only thing that determines what it is the covariance function. Right? And the covariance function looks like this. So you can compute it, and so we take the cross moment minus the product of the first moments, and then what comes out in the end is this thing. So this is the cross moment, and this is the product of the first moments. And the important thing here is that in the cross moment, here is the only place where the sampling distribution plays any role. Okay, and it only plays a role in the w. So I have here expectation with respect to g, and then I can take away 1g and replace it with an f, and so cut one of the likelihood ratio weights. So I get here expectation under the original distribution, the likelihood ratio weight times the indicator x greater than y. And so this is something that if you have done rare event probabilities with importance sampling, this is something that you recognize immediately. So this is the second moment of an importance sampling estimator based on g for computing probability that x is greater than y. Okay. And that's the only thing that comes into play here. So that's sort of where this relation to computing rare event probabilities efficiently is coming from. Okay, so if you apply this, so let's apply this to these two examples, the quantiles and the expected shortfall. You will have a result sort of like this, that so z will be this centered Gaussian process with the covariance function that I gave on the previous slide. And suppose your original distribution has a density which is positive on some interval, say from just below, say, the qth quantile to just above the pth quantile. And then you will have sort of a uniform central limit theorem for your empirical quantiles based on importance sampling, and this will be sort of your limiting random variable. And what's sort of important to notice is you will have a uniform central limit theorem like this, but only in a range sort of from p to q, where p and q are strictly sort of above 0 and less than 1. So you don't get it all the way down to 0. You have to cut a little bit before 0. And then it's the variance of this right-hand side that we will be focusing on. And it's similar if you do, so I will get back to the variance calculation in a bit. I'll just show you the corresponding result for expected shortfall. For expected shortfall, well, let's write this average thing as a gamma p of the quantile. So when you estimate it, you plug in the empirical quantile instead of the true quantile. And then you have a result like this, that your estimator minus the true thing converges to this right-hand side, this random variable, where you sort of apply the function gamma p on the right and on the thing for the quantile. And the thing here that you need to pay a little attention to is that you want to integrate here from 0 to p. And the previous result for quantiles was uniform, but you had to cut off from p. So you have to sort of be sure that what you're doing from 0 to a little level just above 0, that doesn't sort of cause any problems. So you can sort of do the integration all the way down to 0. And for that, you need sort of a condition like this, which is integrability condition on your covariance function. So it's the asymptotic variances that we'll be focusing on. So let's do it first for the quantiles. So for the quantiles, the limiting quantity was this thing, and if you evaluate the variance, well, we do it in terms of the covariance function, and if you take another step, you will have sort of this thing that does not depend on your sampling distribution, and you will have sort of this is the only thing that you can affect through the choice of sampling distribution through the likelihood ratio weight W. And so basically you see that if what would be a good choice for W is to be able to control this thing. So a good choice for your sampling distribution would be to sample from the conditional distribution of x, given that x exceeds its piece quantile. Right? And that's sort of hard because we don't know precisely this conditional distribution, and we don't know the piece quantile. But it gives you some indication what's going on there. So to say this again, sort of what this would indicate is that what is good is to take G to be an efficient rare event probability algorithm for computing the probability that the x is greater than its piece quantile. Okay. And now, of course, since we don't know the piece quantile, that's the thing we're looking for. What you would do is you sort of put in a rough approximation of this, and the rough approximation you could get from say a large deviation approximation. And if you put in sort of a rough approximation for this, then you have to put some requirements on your rare event probability simulation algorithm, so that it doesn't sort of break down because you're sampling with sort of slightly the wrong threshold here. I'll get back to this in just a minute. Okay, so I speak before the slides come up. So now here's the slide for what I just said, right? So if we can, but it's good for fixing notation. Right? So if we can make a guess of the quantile by say UP, and we design an efficient algorithm for computing probability x greater than UP, then if my algorithm is not too sensitive for small deviations of UP, that should be a good choice for computing the true quantile. Okay, and it's sort of similar for expected shortfall. what you have to do is compute the asymptotic variance, and then you get this double integral, and here is the covariance function. So it looks pretty similar, and it's in the covariance function that sort of the choice of sampling distribution appears. So it's going to be pretty similar. So if you can sample this, use a sampling distribution that's somewhat close to the conditional distribution of x, given x exceeding its piece quantile, then this should be efficient. Okay, so now I'm still sort of just vaguely saying that I need a rough guess of the quantile. I need to design an efficient algorithm to compute probabilities of exceeding that quantile. That's the algorithm I will use, and I say it has to be somewhat insensitive to sort of changes of the threshold. So to make this more precise, I can show you some results which are in the regularly varying setting. So suppose that my true tail is regularly varying with the index minus alpha. And then I suppose I can make a rough guess of the quantile by this UP, which is asymptotically equal to the true quantile. So if I have precise large deviations, I expect to be able to invert that large deviation approximation and get a rough guess, which is something like that. And that would be sort of my if I don't do any simulation, that would be my sort of proxy for the true quantile. And the point of the simulation is to improve on that. And then suppose I can design efficient rare event simulation algorithm for computing x greater than lambda for any lambda, and I call this sampling distribution g lambda. And then again, I say this many times now, if this is not so sensitive to the choice lambda, then this will be okay. And now I have to finally say what I mean by that. Right, I put this on hold for so long. So here is what it could look like. So I have my f, which is regularly varying. So what I require is sort of a condition like this one. So what does it say? Well, it says basically the following. So in the numerator, what I have is pretty much the second moment of a important sampling probability estimate, where I design it for computing probability x greater than lambda, but I use it for computing probability x greater than c times lambda, where c can be a little smaller than 1 or a little greater than 1. Okay, so I use my algorithm based on lambda to compute a probability which is sort of a bit off from lambda. And I normalize by, say, the tail at lambda squared. And then this should be bounded by some function function phi of c. And what if I have this, then it's sort of insensitive to sort of c's a bit off from 1. So what I will use really is I will plug in for lambda, I will take my approximation UP, and then it's sort of insensitive because my approximation is a bit off. This sort of says I'm not so sensitive to that. And then what will happen, so if I have this, then the second moment, this asymptotic second moment, divided by the quantity I'm estimating squared, will remain bounded, and you can get sort of a bound, which is this phi evaluated at 1. So that's sort of what it looks like. If I do expected shortfall, I need to know a little bit more about this phi. Okay. So first, in the heavy-tailed setting, I don't really have any hopes to do anything when alpha is less than 2, because if I compute, first I need alpha greater than 1 for expected shortfall to be finite, so for it to be well defined. And to have some second moments, I need alpha greater than 2. So to be able to look at my estimator, the variance of my estimator, I need alpha greater than 2. Okay, and then I have sort of the same condition with the upper bound phi here, and I now require phi to be regularly varying with index minus alpha. So why does that seem to be a reasonable thing to require? Well, if I were to sort of evaluate this precisely when I use the zero variance changer measure, for instance, what will happen if I use the zero variance changer measure? Well, my W lambda will be f of lambda will be my tail. So I will get the tail and I will get rid of the 2 there. And then up here is the probability x greater than c lambda divided by f lambda, which is the probability x greater than lambda. So this is pretty much a conditional distribution of x being greater than c times lambda given x greater than lambda. And if I have regular variation, that should be like c to the minus alpha. And if I do a good algorithm, I should be able to get this maybe precisely c to the minus alpha or constant times c to the minus alpha, or at least regularly varying with the index minus alpha. And so if I have this, then I can guarantee that so the asymptotic second moment divided by the quantity I'm estimating squared remains bounded. Okay, and then of course you ask, well, so these are the conditions, so can I verify it for any algorithm that I know? And I can. But I only looked basically at, so there are not so many efficient algorithms in heavy tail settings. So what I looked at is when you have a finite random walk, just finitely many steps, regularly varying. I looked at the algorithm of Dupuy, Leder, and Wang. And that's quite nice, because then you get this actually to be a constant times c to the minus alpha. So that certainly satisfies this. And with Jens Svensson, we worked on some variations of that algorithm that you can sort of make the big jump in various different ways, and they will also sort of satisfy this kind of condition. But I haven't looked at it for other problems. And here is just some little simulation study to see if it performs well, and it's a little blurred, so you shouldn't read it too carefully. But we worked with this finite random walk to compute expected shortfall for just for Sn, where n is fixed, and we played with some different thresholds, and we compare sort of this algorithm by Dupuy, Leder, and Wang to, and it seems to perform quite well when you have a threshold which is 10, like 1 in 1,000. You get sort of standard deviation roughly 1.8 compared to Monte Carlo, which would be say 8. And if you go further out in the tail, you get a quickly get a much larger improvement. So I should just show you a list of references, and I'd like to point to a paper by Peter Glynn, which is in 1996, which is in a sort of obscure place, and that's why probably it hasn't been very well recognized. But he does this sort of for quantiles in a light tail setting. So that's the only place where I really have seen this kind of things. So I'd like to give your attention to that. And we have a couple of preprints where this is written down. And I'd also like to show an advertisement. Next summer will be the Applied Probability Society conference in Stockholm. It's in July 6 to 8. And here's the website. And during the winter, there will be a possibility to submit. I know many of you are coming there. In the winter, there will be a possibility to submit abstracts also for the conference. So it's a very nice time to visit Stockholm in July. So thank you very much.
Suppose you have a measure which works uniformly well, which works, I think going to be assuming for all levels of rarity.
Yes?
A single measure which works well for all levels of rarity. Can you say about its performance in this setting? For example, tail probability for a given level.
Yes, that sounds very good. So I haven't looked at sort of that particular case, but that should work, yeah.
And do you look at adaptive methods at all when you're adaptively deciding what you do?
Yes, it's not in our paper, but we did some studies because here we are basically saying select a rough guess and then you stick with that guess and you sample from that. But it's kind of natural to have some adaptive thing searching for so what's the best threshold for the next step. So we have tried that empirically. I think I know what the optimal way is, but it's not really written down. That's something I'm working on. Yeah.
Any other questions? Thanks, Peter, again.